Hello, hello, and welcome back to CS500 Design and Analysis of Algorithm. Our focus being on the analysis. Today we're talking about Chapter 3, Average Case Analysis. So in Chapter 3, we will recall the purpose of algorithm analysis and modes of algorithm analysis. Let me share the slides. So purpose and modes of algorithm analysis. We'll talk about a motivating example, namely the example of incrementing a binary counter, which is a toy example that illustrates why our classical traditional worst case analysis, conservative, pessimistic, may actually be overly pessimistic and may give a wrong prediction about the actual practical behavior of algorithms, and thus motivate different modes of analysis, such as average case analysis. We'll discuss and recall another example, namely QuickSort. Now, if QuickSort, as you know from CS300, has quadratic running time, but the practical implementations that we use every day perform surprisingly well without all the overhead of the linear time median algorithm for choosing the pivot. And an explanation is provided by moving from worst case analysis to average case analysis of QuickSort. Then we'll discuss a more sophisticated example, namely the Simplex algorithm for linear optimization. Its worst case analysis turns out to be actually exponential, and smoothed analysis shows that the Simplex algorithm is actually a polynomial time algorithm, and thus explaining why Simplex algorithm performs so well in practice. That's our goal for today. So let me briefly stop the slides. So here, for the purpose of this example, we come up with a maybe artificial abstract cost measure, namely we count the number of bit flips of an n-bit binary counter. So when we increment an n-bit binary counter, some bits remain the same and some bits get flipped. And here we count how many bits are flipped when we increment an n-bit binary counter. And in the worst case, of course, all bits can flip, right? Or almost all. When there's a wraparound, then all can flip, and otherwise almost all except for one bit can flip. But that's a worst case analysis. So here you see an example of an n-bit binary counter and all its possible states, its possible values, its possible bit combinations. And how much does it cost to increment this counter depends, of course, on the value, right? So if we want to increment this value, then 1 bit flips. If we want to increment this value, then 3 bits flips. This 0 becomes a 1, this becomes a 0, this becomes a 0, so 3 bits flips. So that's why the cost of incrementing a binary counter depends on kind of the input, right? And worst case analysis says, in the worst case, almost all bit flips, and that's optimal, right? That can really happen. But it's a conservative estimate. Intuitively, it's very rare for all bits to flip. Most of the time, only 1 bit flips, if you watch here, right? And this is formalized in what we now do, namely a simple average case cost analysis of this binary counter increment. So let's first define the average case cost of binary counter incrementing. That's the average over all possible values there are two possible choices, 2 to the n possible states of an n-bit binary counter, right? And so we need to normalize, so we divide by 2 to the n, that gives rise to the 2 to the minus n. And then we take the sum over all possible values of that counter, that is capital N ranging from 0 up to 2 to the n minus 1. And for each possible value, we check how many bits are flipped when we increment that value, right? So in the worst case, we take the maximum. In the average case, we take the sum and weight that sum with the total number of possible states. And that's average case. And now it remains simply mathematically to evaluate that expression, right? And superficially, this seems complicated, but here's a trick. We change the order of summation. We first count how often does only one bit flip. Then we count how often does 2 bits flip. Or more precisely, how often does the least significant bit flip? How often does the second least significant bit? How often does the third least significant bit flip? So we count all these cases instead. That's a different way of evaluating the sum, which turns out to simplify the calculation a lot. So how often does the least significant bit flip? Well, it flips every single time. Every single time it flips. So that's the average number of times that the least significant bit flips is 1, always. We've already taken into account this normalizing factor. And now we count how often does the next significant bit flip. That only flips every second time, right? So here's no flip, flip, no flip, flip, no flip, and so on. So half of the cases, only the next bit flips. How often does the third bit flip? The third bit flips every 4th time. No flip, no flip, no flip, flip, no flip, no flip, no flip, flip, and so on. So every 4th time the next bit flips, every 8th time the next bit flip, and so on. And if we evaluate this, you see that this is a geometric sum. Well, to be fair, it's a finite geometric sum. Because we have an n-bit counter, but let's be generous and simply extend that. And then we see that this geometric series evaluates to 2. So the average case number of bit flips is strictly less, but arbitrarily close to 2, which is much less than the linear worst case cost. So the average case cost is constant. The worst case cost is linear. And actually, we know the constant, it's 2. An average 2 bits flip only, which is a considerable improvement over our worst case analysis, and also a much more realistic of the actual behavior of bit flips in the binary increment counter. And thus we have formalized our intuition. Intuitively, we already knew that on average, only very few bits flip. And now we've defined and analyzed that on average, 2 bits only flip. So that was our first very simple motivating example. And now we move on to maybe a little bit more involved example, namely QuickSort. As you remember, we introduced and analyzed QuickSort in CS300 Introduction to Algorithms. And there we introduced the cost measure of counting the number of comparisons. QuickSort is a comparison-based algorithm. And we counted the number of swap operations, which was actually basically the same, roughly, up to constant factor. And now, as you recall, the worst case analysis of QuickSort gives a running time of n squared, because the behavior, the performance of QuickSort depends crucially on how the pivot is chosen. Remember, the pivot indicates where we split the array and then recursively sort the 2 subarrays. So here you see an example. let's suppose this is the input to the QuickSort, and let's suppose QuickSort chooses this first number in the array, the number with the first index, as a pivot. Now this number is 31, and in its position after sorting, it's the fourth position, right? So we say split the array according to this pivot. All elements that are smaller come to the left, and all elements that are greater end up in the right. And then we recursively sort the two subarrays. And yeah, this is kind of a good, almost good pivot, because it results in the arrays being split roughly half and half. But we cannot really predict how the pivot will split the array when we choose the pivot only from the position. So here we choose the first element as pivot. We could also choose the last element as pivot, or we could choose the middle element as pivot. But that's the first or last or middle element with respect to the index in the array. So the classical recurrence that we considered when analyzing QuickSort is the running time for sorting an n-element array is O of n for kind of splitting the array, putting all elements less than the pivot to the left and all elements greater than the pivot to the right. That's the overhead. And then the two recursive calls for recursively sorting the subarray that is left of the pivot and the subarray that is right of the pivot. And here you see the cost of sorting the subarray left of the pivot depends on how large is the subarray left of the pivot. And this number is indicated here with this symbol J. And we don't know what J is. And in the worst case, J could be just 1, for example, in which case the resulting, this is will be constant. And this will be the same, basically same cost as here. So in this case, this results in the quadratic running time. Same when J is very large, but we cannot really predict what is J. So to make things more formal, J denotes the quantile of the chosen pivot position. Let me say that again. So we choose a pivot according to its position in the input array, first entry, last entry, middle entry. But what really matters is not the position of the pivot in the input array. What matters is the quantile of the pivot. The quantile meaning how many elements in the array are smaller than the pivot and how many of them are larger. And that's what governs the running time and the recurrence. And in CS300, we designed carefully a way of choosing the pivot so that it has roughly 50-50 quantile. That gave rise to a perfect divide and conquer 50-50. That was the famous linear time median algorithm. But here we perform analysis without such a sophisticated choice. We consider just a naive choice of a pivot, let's say the first element, and in which case we cannot predict the quantile of that pivot choice. In the worst case, if the quantile is 1, then it results in quadratic running time. If the quantile is n, then also quadratic running time. So what can we do here? Remember in this example, the position is 1, but the quantile is 4. So don't confuse these two quantities. But now we proceed from this classical worst case analysis to average case recurrence. So what is the average case recurrence? The average case is taking the average over all possible values for the quantile. So we take a first element, for example, as pivot, and then we consider the average of all possible quantiles of this first pivot. So here's the formula. So here we take the sum again of all possible values of the quantile. The above recurrence is the same. And then we take the weight divide that by 1 over n because there are n possible values for the quantile j. So this is our average case recurrence, and now we need to solve that, which is again only mathematics. The computer science part is done, and we need to solve that, and the solution is O of n log n. And this explains, so this is the average case cost of QuickSort with a naive pivot choice n log n, and this finally explains why naive QuickSort, most implementations these days are actually naive QuickSort, why that behaves so well in practice, because the worst case is rare. In the average case, it has running time n log n. So yes, as I said, solving this recurrence is mathematics, and actually it's a very good exercise and gives you insight into solving recurrences. And now, surprise, surprise, a quiz. So here we'd like to ask you to first verify that O of n log n indeed solves the average case recurrence of QuickSort that we have derived here. So please do not try to derive it again, but instead a purely mathematical task of verifying, of proving that O of n log n is indeed solution to this average case recurrence. That's part A of the quiz. And in part B, I would like to ask you to verify that O of n, linear time, does not solve this recurrence. Again, this is a purely mathematical question. Item B, don't refer to QuickSort or anything. Just verify that O of n is not the solution to this recurrence. And well, if you find that O of n does solve the recurrence, then you have made a mistake. And chances are that you have also made the same mistake also when you proved item A. So in this case, please find the mistake, your own mistake in proving in item B, and then find and correct the same mistake in also item A, so that you have both items correct in the end. So now I'm going to stop recording to give you time for solving this quiz, and then we'll resume. And here we're back. Have you been able to solve the quiz? Have you been able to verify that O of n log n indeed solves the recurrence, and that O of n does not solve the recurrence? Great. Then let's proceed and move on to analyzing the famous simplex algorithm. So first, a little bit background about, or remainder about convex geometry. What is convex geometry about? Well, it's about convex subsets of, let's say, Euclidean space. So let's recall, what does it mean for a subset of Euclidean space to be convex? Here you see some examples, some example shapes in two-dimensional Euclidean space that is on the plane, and some of them are convex and others are not convex. So which ones are convex? Which ones are not? Remember, the definition of convex means that for any 2 points, the connection, the line segment between these points also lies in the set. And you can see this is true for this, and this shape, but not for this, because the line segment between these 2 points lies outside of the shape, and same here. So these two are non-convex. And one particular class of convex subsets of Euclidean space are half spaces. half spaces in d-dimensional Euclidean space. And just to be precise, I'm talking about affine half spaces, that is, half spaces that need not pass through the origin. They can be moved, they can be shifted away from the origin, or yeah. So here are two examples in 2 dimension and in 3 dimension. An affine half space is everything here, so it's infinitely large. And in 3 dimension, affine half space is everything here below this point, below meaning in this direction. And here you see it's only a cube cut out, but again, half space in 3 dimensions is infinite in 3 of the 4 directions. And you see also how we can formally describe and parameterize a half space. Namely, there's a normal vector, something that says everything. So the boundary is a plane. Here it's a line, and here it's a plane. And the higher dimension is the hyperplane. And we can describe such a plane or hyperplane by its normal vector, the vector that is orthogonal to this plane. And since we're talking about affine shifted half spaces, it means there's also an offset, a distance from the origin to the any point, the point in the plane that is closest to the origin. And mathematically, this means we have two parameters, one orthogonal vector, not necessarily normalized, that we call A, and an offset B that describes the distance of the point in the plane to the origin if A is normalized. And then the affine half space is a set of all points U, vector notation, whose inner product with that orthogonal vector A, inner product, is less or equal to B. All points that are closer than B to the origin in the direction of A. That's the intuition. So yeah, you probably know all this, but just a reminder from maybe discrete mathematics. And now we want to move on and consider not just one half space, but several of these half spaces. Let's say n such affine half spaces, as you see here. How do we describe them? Well, we describe each affine half space by such a orthogonal vector, and we combine all these orthogonal vectors into one matrix, which is now a matrix of format D times n. And similarly, the offsets, each one being a real number, all the n offsets are combined into one vector, which is now an n-dimensional vector. And we take all these affine half spaces, n half spaces, and we're interested in the intersection of these half spaces. And as you can easily verify, the intersection of two convex shapes is again convex, and therefore the intersection of these n affine half spaces is not an affine half space, but it's a convex set, and convex sets of this form are called polytopes. So we take the intersection of these n affine half spaces, and mathematically, this means we take the conjunction, the set of all vectors that satisfy all these n linear equalities, and we can write that concisely as saying that the matrix multiplied to this vector u must be less or equal to the vector of offsets component-wise, right? So here, left-hand side is an n-dimensional vector, right-hand side is an n-dimensional vector, and we require that each entries in these two vectors on the left side must be less or equal to the corresponding entry in the vector on the right side. So that's symbolically, algebraically, and geometrically gives a very nice picture like this. So this is an intersection of affine half spaces. Each phase here comes rise from one affine half space. So this means all points below this, the hyperplane below this, and here all that are right from this, and so on. So there's really an intersection of finitely many affine half spaces, and this is what is called geometrically a polytope. And what the simplex algorithm does, it solves an optimization problem within such a polytope, namely a maximization problem. So affine optimization is the problem not of finding the whole polytope, which is infinite, right, in general, but instead of finding the point that is has the largest x-coordinate within this polytope. So input, well, following our paradigm of formally specifying the problem, input is n affine half spaces corresponding or parameterized by such a d times n matrix and an n-dimensional vector. And the output should be the largest value in the intersection of these half spaces. So geometrically, this means how far up can we go? Without much of generality, we can suppose that this is the x-coordinate, and then the largest x value is how far up we can go in that polytope. So in general, the point which attains that maximum is not unique, but the maximum is always unique. And if we make some non-degeneracy assumption, then also the point is unique. And symbolically, algebraically, this means we're not interested in the set of all points in that polytope, which is infinite, but in the largest x value, that is the largest value of the first coordinates of all points in that polytope, the largest, the maximum. So it's an optimization problem. And right, so the simplex algorithm solves that problem. And here's a brief, concise description of the simplex algorithm. Actually, to be fair, there are many simplex algorithms, but they're share the same structure. So sometimes it's called the simplex algorithm. And the algorithm starts with any vertex of this polytope, and how to find such a starting vertex is, well, we're going to ignore that question. We just started some vertex, maybe this one. And then the simplex algorithm chooses a neighbor vertex, right? Like this is a neighbor vertex, this is a neighbor vertex, but differently following any so-called ridge or edge, to be more precise, any edge from the starting vertex to another vertex. And the simplex algorithm chooses such a neighbor vertex and then repeats. And the neighbor vertex, that's a choice of the simplex algorithm. It should be a vertex which has a larger x value so that the simplex algorithm moves upwards. So for example, it could move to the highest neighbor vertex or to the closest neighbor vertex that is higher. There is variance. And then it repeats here from this vertex, move to this neighbor vertex, from this vertex, move to this neighbor vertex, from this to this, to this, to this, following this right path. And then here it ends because then from here it cannot move on higher. So this is where the algorithm stops and returns the x value of this vertex, and thus have solved the optimization problem. It's a very geometrically very intuitive and famous algorithm. It was developed in 1946, 1947 by George Dantzig. So George Dantzig was born in 1914 and lived until 2005. And yeah, he's there's a famous anecdote revolving around him, namely in 1939. So before he found the simplex algorithm, he was already kind of famous, because at that time he was a student of Professor Neyman, and he arrived late in class. Can you imagine that? He arrived in class late, and he found that Professor Neyman had written 2 problems on the blackboard. And Danzig assumed that these were the homework assignment. So after class, he went home and tried to solve these problems, and he found that these 2 problems seemed a little bit harder than usual. So a few days later, he submitted his solutions to the 2 problems. Late submission, even worse. And it turned out that these were not homework assignments, these were open problems. So George Danzig had solved 2 famous open problems. And later, Neyman suggested that he just choose one of the problems as PhD thesis, and this is how George Danzig graduated without actually formal PhD thesis. And this anecdote actually made it to the Hollywood movie Good Will Hunting. So here you see Matt Damon, who played a role in that movie, but the story behind that is actually George Danzig. Right, so let's now move on to analyzing the simplex algorithm. And there are various interesting questions that arise with the simplex algorithm. So for example, right, so there is always a path from any given vertex to the topmost vertex, to the vertex with largest x value. That's a simple connectivity question, right? And this path can be found, such a path can be found greedily, just keep moving upwards. But there are various choices of greedy moving upwards, right? Here we can move this way, or here we can move in this way, and then continue. So there were various choices how to choose the neighbor vertex. And Danzig's original algorithm chose the highest neighbor, but it could also choose the closest neighbor, various choices. So as I said, there always exists a path, and any path greedily chosen leads to the top vertex, but the question is, how long is the path? Can we always find a path of length that is at most polynomial, right? That's our choice, that's our desire. Short paths to get to the top value to solve the maximization problem. So question A, does there always exist a short path, a path whose length is at most polynomial in what? Well, we have 2 parameters here, right? The number n of affine half spaces that define this polyhedron, and the dimension d in which this polyhedron lives. And we want the length of a path to be at most polynomial in those 2 parameters, or equivalently in the sum of the 2, or in the largest value. This is all the same, mathematically speaking. So, and once we know that such a path exists, then we can ask the next question, can we find such a path? Can the simplex algorithm find such a path by, for example, by moving always greedily to the highest neighbor, or to the closest neighbor, or any similar kind of local rule, right? So these rules only look at the current vertex and look at the neighbor vertex. They're at most polynomial number of neighbor vertices, and choose one, and then how to choose that. So that's the 2 questions. And and if we can answer both questions positively, then it means that simplex algorithm has a polynomial runtime, right? But as it turns out, these questions are famously difficult. The answer to the question A is even still unknown. It's a famous open question, whether there even exists such a path of polynomial length. It's not known, nor are there counterexamples known. So what is known is an upper bound on the length of such a path, which is slightly superpolynomial n to the log d. So you see that here d is in the exponent, but only the logarithm of d. So this is not polynomial, but it's not exponential either, right? It's the exponent is not d, it's only log d, so mildly superpolynomial. And this bond was proven in 1992 by Kalai and Gleitman. So it's not known whether there always exists a polynomial path of polynomial length, and therefore it's even less likely to find an answer to the question B, because if we don't know the path exists, then how to algorithmically find such a path is even more a mystery. And indeed, already 20 years before Kalai and Gleitman, Klee and Minty constructed counterexamples to the simplex algorithm, where the simplex algorithm actually makes an exponential number of steps. It makes a long winded spiral moving until arriving at the top. Although in the Klee-Minty cubes there do exist short paths, they only show that the simplex algorithm greedily does not choose a short path, but chooses an exponentially long path. And these Klee-Minty cubes are basically, yes, they're start from a cube, and a cube, you know, has an exponential number of vertices. In dimension d, it has 2 to the d vertices. And then Klee and Minty kind of slightly perturb that cube. And here you see a picture in red is a 3-dimensional cube. And the Klee-Minty cube slightly perturbs every single vertex of this cube in such a way that there's a shortest path, right, from bottom to top, very short, but the simplex algorithm chooses this, and then this, and then this, and then this, and then this, and this. This is basically like a Hilbert cube, if you know what I mean. So it takes a very long path to reach the top, although they are short paths. So that means that the original rule from the simplex algorithm, local rule, is not suitable, but maybe some other rule is. And there are many other rules that people have considered. And one rule I'd like to point out is the so-called shadow neighbor rule. I'm not going to formalize that. Just let me mention that also here, variants of the Klee-Minty cube have been constructed, where even with this modified rule, the shadow simplex algorithm makes an exponential number of steps on some cube which has polynomial diameter. So that's bad news, right? So that means the simplex algorithm and its variants, as we know, have exponential runtime in the worst case. And this kind of contradicts experience, because in practice it seems practical experience suggests that the simplex algorithm is very efficient polynomial time and often even linear time, so that the theoretical analysis, worst case analysis of the simplex algorithm seems to disagree with the empirical practice. And as you know, here in chapter 3, we're talking about average case analysis for exactly that reason, because worst case analysis sometimes gives a conservative, pessimistic overestimate, as we saw with the binary counter incrementing, and as we saw with the QuickSort analysis. So maybe the same happens here. But when we try to perform an average case analysis of simplex algorithm, then we're faced with a problem. What is average at all? So remember that the input to the simplex algorithm is a matrix and a vector. Now, what is the average matrix? What is the average vector? Certainly not a random matrix, certainly not a random vector. That would be that's not how instances arise from practice, not a random matrix and random vector, but instead we have a kind of geometric intuition behind that. And this is what we now want to talk about, so-called smooth analysis. So smooth analysis is kind of a variant or adaptation of average case analysis to the case where we have infinitely many possible inputs, right? So when we analyzed binary counter, we had exponentially many possible states. When we analyzed QuickSort, we had n factorial many possible input arrays. But here we have infinitely many continuum cardinality many inputs. And this is where smooth analysis comes into play. And for smooth analysis, we make a small relaxation. We're not interested in finding the largest x value in the intersection as traditionally, but we allow for some approximation as long as this approximation satisfies a certain approximation ratio. So this is something we'll talk about a lot more when we talk about approximation algorithms later. But for now, let's just take it informally, approximating the top largest x value up to some, let's say, multiplicative factor 1 plus sigma. And here, the following variant of a simplex algorithm is considered. Before starting with some vertex, we first perturb the half spaces slightly. Slightly meaning, again, by some sigma or delta or epsilon. And it can be shown that in most cases, such a slight perturbation indeed affects the largest x value also only slightly. There are several technical details to be taken into account, but that's the general idea. So we perturb the half spaces, and then we run the simplex algorithm, and then we obtain an approximate solution. And the question now is, what is the running time of this algorithm? It's a variant that first makes this random perturbation to obtain an approximate solution. And geometrically, you can imagine it like this. So the original polytope maybe have looked like this. And after the perturbation, it may look like this. Now this picture is slightly misleading because, as you can see here, the combinatorial structure remains the same, only the shapes slightly change. So in particular, all the paths here and here are basically have the same length when you count the number of steps, but this is misleading, and this is due to the low dimension, 3-dimension. I have a hard time showing you large dimensions like dimension 100. So, but trust me that when we perturb the half spaces slightly, then in higher dimension also the combinatorial structure may change, and also the class of family of paths from lowest to top vertex will in general be different from the class of paths here. And this is where really the the new simplex algorithm also comes into play. First, different class of paths, and secondly, climbing upwards can be different. So if you recall, the Clementi cubes had a slight perturbation, and now if we apply to that this perturbation, then in general, this will kind of destroy the original perturbation of Clementi and result back into from the worst case into good cases. And indeed, this was formally proven by Teng and Spielmann, famous paper, Journal of the ACM, where they proved formally that after random Gaussian perturbation of variance sigma, so this is the formalization of this step 0, perturb the half spaces slightly, meaning random Gaussian perturbation of variance sigma, then the so-called shadow boundary pivot rule, that's one of the variants of the rule that I mentioned before, makes a number of steps that is polynomial in all the quantities they were interested in the dimension, in the number n of half spaces, and in the perturbation. So that means we get a good approximation up to this approximation factor. So I'm not going to present the analysis here. That's pretty involved and famous. The algorithm, on the other hand, is very simple. Just make a slight perturbation and then execute the original simplex algorithm with the Danzig's rule replaced by the so-called shadow boundary pivot rule, which I don't emphasize here. So that also motivates us later talking about two different classes of algorithms and their analysis, namely approximation algorithm on the one hand and randomized algorithm on the other hand. So for now, let's take this as motivation for studying this and analyzing such algorithms later. And I want to close and conclude with an abstract view on worst case versus average case complexity. So here you see a hypothetical picture. You see the input space here. Consider input space being a two-dimensional space. In general, it's of course an abstract space that cannot even be visualized. And suppose that the algorithm on some usually performs very well, but in some cases it performs very badly, takes a lot of time. So here this is the runtime and this is the input space. And so worst case analysis says this is the running time of the algorithm. But you see here from this picture, this gives a conservative, pessimistic, a strong overestimation. Intuitively in this picture, most of the time the algorithm is actually very good, right? So that's worst case analysis is this peak, but this is overly pessimistic, overly conservative, whereas average case is somewhere like here, right? If you take the average height, since these peaks are very thin, they contribute very little to the average height, right? So the average height may be somewhere here like 40 or so, or 50. So average case analysis gives a better prediction, a more realistic prediction of the behavior of the algorithm, more uh, optimistic than the worst case. So that's worst case versus average case. And now how does smooth analysis fit into that? In smooth analysis, we kind of don't take the average over the all intimate space, but only locally over small balls around the worst case input. So we kind of average out these peaks, which makes them a little bit broader and much lower. So you see here, the original high peak and these original high peaks all become thicker but lower. And this is what smooth analysis is about. So to conclude, in this chapter 3, we have talked about the purpose of algorithm analysis, namely to be able to predict the behavior performance of algorithms without running them on all possible inputs, and modes of algorithm analysis, worst case, average case, and smoothened case. Or in this chapter, later we'll talk about amortized case, expected case, and so on. Motivation, we discussed incrementing a binary counter where we saw that worst case analysis gives a serious overestimation of the number of bit flips, whereas in the average case, only 2-bit flip constant cost as opposed to linear. And we made an analysis of QuickSort, the naive QuickSort, and we saw that in the worst case, it had quadratic running time, but with any choice of the pivot, actually, the average case favor of QuickSort is O of n log n, which explains why it behaves so good in practice, although the worst case analysis says it doesn't. And we ended with discussing convex optimization and Danzig's simplex algorithm, which again has an exponential worst case performance according to Klee and Minty, but smooth analysis showed that in the smooth case, it has polynomial running time, which explains what people have been experiencing in practice, that it behaves very efficiently. Where smooth analysis is a hybrid of worst case and average case analysis that inherits advantages from both. So that's all for today, all for chapter 3. Thank you very much. And as usual, I will remain online a few more minutes to answer your question, and then we'll see again next time talking about chapter 4. Thank you very much.